Okay, welcome to Chapter 20, the start of the particles chapters really. And when we're talking about particles here, we're talking about small particles. So we're going to look at how our history and our ideas have changed of what things are made from. However, what we're effectively doing is just going deeper and deeper and deeper. And every time we go deeper within this Russian doll setup of what matter is made of, we find smaller and smaller levels. And we're effectively doing the same experiment over and over again, just at higher and higher speeds. Okay, so we're going to explore some of the ideas about subatomic particles like quarks and leptons, and we're going to go all the way through from that bigger idea and the processes and properties about it. So, 3 chapters really that do this. Chapter 20 is mainly factual, it's quite factual stuff, so it's the particle physics and the nuclear structure itself. So we'll have a look at those bits really. So we know a little bit from GCSE. You might know a little bit of detail about it, but we're going to go much deeper. Some of this is being known if you have been watching various YouTube videos. It will get you into that area, but we're going to go into some bigger stuff and look at the patterns behind it. So we're going to start off with the bit that really matters, is being able to speak the same language. So just be a little wary if you are taking chemistry, because these are the phrases we use, and I'll try and pick out the differences between them so you can see that. So what are the bits that matters? Well, we are talking about the Bohr model of the atom, so the standard model that you learned at GCSE, using the idea of shells as our basis. Okay, so that's going to be what we're looking at. Now please notice we are not, like with chemistry, looking at relative amounts like you did at GCSE. We're looking at actual amounts. So all in the front of your data book. Okay, so get that handy. In the front you'll find all the key bits of data here, and you'll find some interesting information down here. I will introduce you to a few other things as well, like strangeness. Okay, so we'll bring all those in. However, parts of this topic you may need to do a little bit of research. So, if we look at our fundamental constants, what we have at the start is something called the elementary charge in your data books. What we're talking about is the charge that is shared by all particles at an atomic level. So we go into them, they have those values. So what have we got? We are talking not +1 for protons, but plus 1.6 times 10 to the minus 19 coulombs. Okay, the electron, exactly the same, which is kind of curious, which leads us into this whole chapter. Why are there so many similarities in these different things? Okay, and crucially, again from the name, neutral for neutrons. So names themselves, they're kind of hinting at these things. Electrons came from electricity, positive charges, neutral charges. Everything with an on at the end is a particle. Okay, so all of the particles share the same basic structure. Right, on the data sheet as well, okay, we have masses which are not relative to each other, so we want proper SI units for masses. So 1.67 times 10 to the minus 27 is the mass of protons, and for neutrons as well. However, they do start to differ when you become more precise. So when we're looking at things like changes in mass within atoms, we need to be far more precise than this. So at this level, and I'll put it into brackets, so most of the time we don't need to worry that they're slightly different, but we will for certain aspects of it. The neutron is slightly more massive than the proton. Okay, and the electron itself is on a completely different scale, so 10 to the minus 31. Okay, so these are around about 10,000 times more mass than those on that scale. Obviously that's almost 10 to the 30, so around about 1,000 times. Now, again, these are the only values we have for these. We don't physically have a size for electrons. We have not yet been able to measure the size of it. ignoring the fact that potentially it has wave-like properties as well, we have not actually gone down small enough to measure that. These we do know roughly, but again, it's not the properties that matter. The properties that really matter are about charge and mass, which is how they behave. Now, the Bohr model, very similar to effectively the astronomy model, solar system model. Just to give you some idea though, the scale for atoms, if we were to make the sun and a nucleus the same size, we are well over twice as big on this scale than the outer reaches of our solar system. Okay, so the scale is enormous. If you were to go into the largest football stadium you could think of, the nucleus is about the size of a pea on the centre dot. It is tiny. Most of the atom is space. It is a vacuum. There is nothing between the protons, neutrons, electrons, etc. It's space. However, and that's why we don't worry about size, how far they are apart does matter. Okay, so we don't necessarily need the size of the actual particles themselves, but we do need to know about this spacing, and that's kind of crucial for a lot of what we do. Okay, standard notation, again, just be wary if you're doing A-level chemistry, then these are reversed on the OTR course. So A and Z are the standard ways of notifying things, slightly different numbers. Z is kind of used at GCSE, so some of you may have used the proton number. It's effectively down to that idea of number of protons. We do like it nice and simple. Okay, for us, okay, we are looking at protons only. We are looking at the behaviors. We're not looking at how they compare to your standard atom. Okay, because there is no such thing as a standard atom for us. We're looking at individual atoms, so we need to know the number of protons. Please notice that the top number, the large number for us, is the nucleon number. Okay, so again, it is nothing to do with mass. Okay, it is not relative atomic mass. That makes much more sense with chemistry because you're not talking about individual particles themselves, not individual atoms, not individual isotopes, not individual nuclei. You're talking about a huge quantity of numbers, hence the use of Avogadro's in a lot of their calculations. For us, we are looking at a much, much smaller scale, so we actually want details of that atom that we're talking about in the question, not a different atom. Okay, so the idea of this will pick up on a little bit because it does link in with isotopes as well, but basically, yeah. Total number, again, it's not genius, it's total number of particles in the nucleus, and we will build this up, but basically it is effectively for us A is Z plus lowercase n. Number of protons, that's your number of number of neutrons, that's your number of protons. You put them together, you get the total number in the nucleus. Okay, so how does that differ? Well, again, sorry if I'm teaching suck eggs here a little bit, but if we take, for example, looking at relative atomic mass for things like chlorine, okay, it has, even at GCSE, it had 35.5 as the relative atomic mass. Now, obviously, for number of nucleons, that is nonsense. You can't get 35.5 particles in your nucleus. So for chemistry, it's all about the average. Okay, and the basis is here. There are two main types of chlorine, two different masses of chlorine atoms, which have different proportions, and because of that, the average of them comes out at 35.5. Okay, for those that are in the let's say studying A-level chemistry will know that most of the relative atomic masses at A-level are not whole numbers. Okay, but for us they are about that atom, as I say. So What's important? Well, we're going to keep talking about isotopes most of the time. We're also going to talk about ions because we're talking about ionization. So again, it's one of those where you just need to be really clear on the language. Okay, so isotopes of an element, again, just have different numbers in the nucleus. They are still the same element, they still have the same value of Z, but they have different numbers of neutrons. Okay, so again, commonly you're asked to define this. What is meant by an isotope? It's a particle with the same number of protons, but different number of neutrons. No need to discuss mass. Right, okay. If we just move on a little bit, then we can actually pick up on what really matters itself, okay? And we can start looking in the details inside. So, key thing I wanted to just finish up on, nucleon number tells us the mass and structure of that. And again, it's about that atom, so it's not about that isotope, which is a quantity of particles, quantity of atoms or elements, quantity of elements. It's all about single individual ones.